I promised you to prove that the limit of this process actually verifies the original equation of Fedosov. So let me begin with this. Of course, you can just believe me that this limit verifies this condition, but you need not. Okay, so we have zeta, which verifies the equation zeta is equal to zeta 0 plus delta minus 1 of nabla zeta plus 1/2 zeta comma zeta. So I claim that, first of all, delta minus first zeta is equal to 0, but that is automatic because delta minus first of zeta 0 is equal to 0, and delta minus first square is also 0. Second, zeta 0, 0 is also equal to 0, and that's because zeta 0 has this property. But also the correction to the second term of this equation begins with delta minus first. And delta minus first takes values in the space of elements which verifies this condition. I mean, delta minus first of A, 0, 0 is always equal to 0 for all A. That's just a definition of delta minus first for you. So, what we can do, we can use this equation to check that, how do you call this, delta zeta, that's the curvature of the connection nabla plus delta plus commutator with zeta, right, is equal to square root of minus 1, maybe with minus sign, made by h bar omega plus phi. That's what we need to check. But let us consider the difference A equal to omega zeta minus this prescribed term. First, I claim that delta minus first A is equal to 0. And that's easy because what do you call this? Delta minus first of omega zeta minus minus square root of minus 1 h bar omega plus phi, right? So what is it equal to? So this zeta, this omega zeta, if you remember, is equal to omega 0. That's delta minus first of, sorry. That was just Fy, as far as I can remember, right? Plus nabla omega y plus, I think, what was it? There was some third term which I don't remember. It was something very simple. Because in Canada, can anybody remember this? Oh yeah, minus phi, just minus phi. Sorry. Yeah, but I think it was not minus, but rather plus in any case. Okay. Then, what was else? What did we have in omega zeta? We have delta zeta with plus, right? Maybe it was minus plus nabla zeta. It was part of this element, and also a square root minus square root of minus 1, right? It's this. Yeah, I think it was this. And also we had 1/2 of zeta zeta. Yeah. Now, this term, yeah, I also forgot that we subtract. What we subtract? Minus square root of minus 1 by h bar omega plus phi. So that's the first. This first long term is precisely this. What we get. And this is this. Now we subtract this and these. These two things disappear. Right? And we eventually come up with the equation delta minus first of omega 0 right. I know it was no phi, it was something different. I'm sorry. Oh. Oh no, that was, sorry, it was my fault. I think it was like this, actually. I just don't remember what was this term. What was this omega? Yeah, it would be probably easier just to omit omega 0 altogether and just write down everything correctly. Sorry. It's always hard to remember all the formulas. So it's probably easier to write down everything by hand. So when we get Fy, right? This comes from this. And we also have nabla omega y. That comes from the commutator of this and this. This element gives us this term. Right? This element, this and this, gives you this term, right? This and this give you this term, right? And also, I forgot that there was this delta z, delta zeta. Ah, no, the delta zeta is here. Sorry. And yeah, and we subtract minus square root of minus 1 divided by h bar omega plus phi. Okay, nice. That's it. That's what I have inside. So all these terms, they correspond to the first part of this equation. I'm sorry for me taking so much time to restore it, but it actually was due to the fact that the formula was pretty cumbersome. But now we can eliminate this term. We collect these, and these terms into omega 0, as by definition, right? And what we get, we have this formula, delta minus first omega 0 minus delta zeta, right? Plus nabla zeta plus 1/2 commutator of zeta and zeta. Nice. Up to the sign, as usual, but I think this time the signs are correct. Yeah. Yeah, that's correct. Now, when I apply delta minus first to omega 0, I obtain zeta 0 by definition. Also, since delta minus first delta, since delta minus 1 of zeta 0 is equal to 0, and also zeta 0, 0, 0 is equal to 0, we have the delta minus first applied to delta zeta is equal, without 0, is just equal to zeta, right? And also we have plus delta minus first of nabla zeta plus 1/2 zeta comma zeta. But if you look into this, that's precisely the equation. So we get 0 as promised. Okay? Nice. What we also have, it is that the operator D applied to A is also 0. And that follows from the fact that omega zeta is in fact the curvature of D. Hence, by Bianchi identity, D omega zeta vanishes, right? On the other hand, D applied to minus square root of minus 1 divided by h bar omega plus phi should be equal just to the Theorem differential applied to the same pair of differential forms, right? And that's because, again, these elements there in the center, omega and phi, and the difference between D and just the Theorem differential is just equal to the commutator. So the commutator vanishes and we just have the Theorem form. So Theorem differential. And that's 0 because this is closed and this is closed by definition and by condition. Now we are able to prove the ultimate fact we need. That is to see that A is identically equal to 0. And to this end, I observe that A 0, 0 is equal to 0. Well, just because it's a two-form, it's homogeneous two-form, it has no zero component, right? Hence, delta minus first delta A, delta plus delta, delta minus first A is equal to A. But we also know that delta minus first A is equal to 0, right? So we have A is equal to delta minus first delta A, and what we do, we take delta minus first and observe that this is equal to dA. Because you remember d, not just d, sorry, not just dA. It's dA, okay, we know that dA is equal to 0, but dA is equal to nabla A. I think minus probably, or plus or minus, delta A plus zeta A, right? So we can now use this equation to express delta A as nabla A plus zeta A. And again, this element has the same grading in terms of Weyl algebra as A. And this also has the same gradient as A, or greater than A, because zeta has a gradient 1, right, or greater than 1. It's not 0. And delta minus first increases the gradient in Weyl algebra. So we see that the gradient of A is greater than the gradient of A. And that can only happen when A is equal to 0. And that's what I promised. It's precisely the formula we wanted. That's more or less the end of Fedosov quantization, although there are lots of details which still need to be discussed. Let me very briefly go through these details. Now, first of all, I need to identify the space of flat connections with the space of all functions. Sorry, flat sections. Flat sections, sorry. What did I say? Of W hat C H bar M omega with C infinity of M with coefficients in H. Now that's easy. To this end, we do the following thing. We consider the chain complexes, or probably better to say cochain complexes. And there are two cochain complexes. First, the complex of sections of this vector bundle, Weyl vector bundle, with the operator given by abelian connection, or Fedosov connection, which is known now, which is called now. These abelian connections of Fedosov are now called Fedosov connections, of course. And that's deserved, I think. And there's another complex with the same space of cochains, but with different differential. Namely, we have the differential delta, which also sends all the elements here to the elements in W1 in one forms. Because as you remember, this differential delta looks as this formal sum in local coordinates, right? So it always sends the sections of the Weyl bundle to the differential one forms with coefficients in Weyl bundle. It turns out that these two complexes are actually isomorphic. I'm not going to prove this. The proof is pretty much the same as before. We just construct a map Q from lower row to the upper row, and from the upper row to the lower row, using the same idea, using the operators delta and delta minus first. However, if you're familiar with homological algebra and homological perturbation theory, then this is now, it is almost evident that the possibility to do this is almost evident, because this operator D looks like a perturbation of the operator plus or minus delta doesn't matter. Perturbation it with something of lower degree. I mean, the degree here is the degree with respect to the Weyl filtration, to the Weyl gradient. Delta raises the gradient by 1. And all the other terms here, they either do not change it or even lower it. So it's actually, sorry, it's opposite. It's actually this lowers and this either increase it or do not change. So in some sense, they are infinitesimal with respect to the first element here. And that's what is treated by the homological perturbation lemma. When you have a complex with a differential C, and you have a differential delta in this complex, and then you have the same complex probably, but the differential delta plus something infinitesimal. And then you can show that if you're allowed to pass to limits with respect to these infinitesimal terms, you're always able to construct chain homotopy between these two spaces with respect to these operators. So that's precisely this chain homotopy which appears here. I'm not going to talk about these details. You can find in my lecture notes. But now it will mean in particular that the kernel of delta as a map from W hat 0 H bar M to W hat 1 H bar M will be equal to this, will be isomorphic to the space of flat sections with respect to D in W0 H bar M. Right? And it is easy to find the space of this, this kernel. It's easy to find this kernel. Hello? Yeah, so what is the kernel of delta? Any element here looks like a formal sum h bar to the power p a p I of x y to the power I. A kernel would mean that if you take this element differentiated by y and multiply by dxi, and take the sum over I, you'll get 0. But it only happens, since all the xi are actually linear independent, it only happens when this expression does not depend on yi. And that means that API is equal to 0 for I not equal to 0, 0, 0. Hence, the kernel is equal to the space infinity of M with coefficients in h bar, extended by this formal variable h bar. And this isomorphism now, which is denoted by Q, gives you the inclusion, the embedding of this space inside the sections of this Weil algebra bundle by flat sections with respect to D. As we have discussed last time, the space of flat sections is in fact a subalgebra inside the Weil algebra bundle by the space of sections. And we can now introduce the star product on the space of formal power series by taking F star G to be equal to the inverse Q minus first, QF multiplied by QG. Here Q is this isomorphism between the kernel of delta and the kernel of D. Step 2 would be to check that all the axioms of the star product hold for this construction. Well, the h-bar linearity is evident because that was the way we constructed these maps. All the maps we constructed were h-bar linear. So that's not a problem. The first term in the expression for F star G is also easy to find. You just need to remember that Q always begins with just the identity operator, and then you have some correction terms. Hence, this product always begins with F times G plus something. It is a bit more complicated to show. That the first term after this will look like the Poisson bracket of F and G. Well, it's a bit easier to show that the commutator of F and G will be equal to h bar times the Poisson bracket of F and G plus some correction terms. To this end, it is enough to observe that this formula actually holds in Weil algebra, if you just write down the Weil algebra explicitly, then you have it. And then you look into the way Q is defined. I'm skipping this altogether. Sorry for. It's very technical. In fact. Huh?
The importance of these space of flat sections to be a subalgebra, that is the thing that we have been.
It is a subalgebra just because the space of flat sections is always a subalgebra.
It is to take Q inverse.
Yeah. Yeah, Q inverse is always Q inverse always exists. You see, because Q is an isomorphism of complexes.
But I need the product to be in the image.
Yes. But to be sure that the product of the image of two elements from the kernel of delta is in the kernel of D, we really need this Leibniz rule. The fact that all the correction terms, that all the terms that appear there come from certain bidifferential operators, it also appears from the fact that Q is an iteration of D, in fact. Is certain iteration of D with certain coefficients. And D is a differential operator if you look in local coordinates, right? So Q of F will look like certain collection of H bar to the power P, certain differential operators, P-fold differential operators applied to F times to Y times Y to the power I, right? When you take this product, you just obtain QF times QG equal to H bar to the power P by differential operators of F and G, which BP, they are just collections of dP with certain coefficients. Nice. It's also, but as far as the unity is concerned, it was a technical condition. We could actually omit it, but in this case, that's much easier than all the rest. So it's almost a straightforward thing to see that Q of 1 will be equal to 1, just because all the correction terms will vanish, all the differential operators applied to D to 1 will vanish, except for the first term. So 1 star F will be equal to F will be equal to F star 1. Okay. So this is in fact a star product. The associativity follows directly from the construction I gave. Now step 3 is to classify these star products up to the equivalence relation. And that's probably the most interesting part of the whole story, because here we will see, at least I'll sketch it, that this, the space of the set of classes is closely related to the topology of the manifold M. Namely, it is evident that two star products obtained in this way are equivalent if and only if the corresponding flat sections, abelian sections, are equivalent. Now that follows from the fact that that the star products can be identified with the usual Weil product in the space of flat sections, which correspond to the connections D1 and D2, right? So if we know that these two connections are equivalent as connections, you know the two connections are equivalent if there is a gauge transformation of the bundle which sends one of these connections to another, right? If these two connections are equivalent, then the space of flat sections will be isomorphic. Isomorphic in the sense, the isomorphism will be given by this gauge transformation. This gauge transformation will not be just isomorphism of linear spaces, of vector spaces. This gauge transformation will induce the isomorphism of algebras of flat sections. You see, of course, all these flat sections are linearly isomorphic, just because they all are isomorphic to the space of functions on the base. But if we know that these two flat connections are isomorphic as flat connections, then we can use this gauge transformation to define the isomorphism of the algebras of flat connections. Because gauge transformation preserves the product. You see? Yeah. Gauge equivalent, let's put it this like this. Gauge. Because gauge transformation preserves the product. Now, when you have a gauge transformation, this gauge transformation acts nicely on the curvature. So in our case, the curvature of the first abelian connection looks like minus square root of minus 1 divided by h bar omega plus phi 1. Right? This is, sorry?
This is only we have, how is the implication from the left to the right? The equivalence?
That's section, connections.
If we have equivalent star products, how do we find the gauge equivalence?
Oh, that's a bit more complicated because you need to raise this equivalence map from the space of functions to the space of flat sections using the same Q. You use Q, so if you have a transformation of space of functions, then you know that the space of functions is actually isomorphic to a subspace in the space of connection, or sort of sections. Then you use this isomorphism to raise these maps to the space of connection, or sort of space of sections, right? And then you can see that this transformation is in fact given by a gauge transformation of this Weil algebra bundle. That's actually pretty technical. You see, there are lots of technicalities there. Actually, all the details of this construction can be found. I think the only source which gives all details, or almost all details, is the book by Fedosov himself. This is I think, 400 pages long book. And approximately at least one third of this book is dedicated to the details of all this construction. So 130 pages about so, where all the details are meticulously explained. It's pretty dull, I would say. Okay, but in any case, you have the curvature. When I say curvature of an abelian connection, of course I mean those elements which show up in inside the commutators, because the curvature is operator of that connection. The curvature of that connection as operator will always be equal to 0, right? But inside the parenthesis, inside the commutator, we have this element, and the curvature of D2 will look like square root of minus 1 divided by h bar omega plus phi 2. So if we have a gauge transformation which sends D1 into C minus first D1 C, which is equal to D2, then D1 squared will be sent into, so C is a gauge transformation, so it's just degree 0 form, right? But then we'll have C minus 1 DC here, plus C minus first curvature of I think it's oh sorry, it's yeah, like this, DC minus 1 DC, and also C minus first curvature D1 C, something like that, right? But now this will be just equal to the same expression, because this element is in the center and this element is in the center. So they cancel, this conjugation disappears. And we see that the difference of this and the curvature of D2, which is this, right, will be equal to phi 1 minus phi 2, and it will be equal to dc minus first dc. And that's closed. That's not just closed, it's exact. And here is the conclusion, which is probably the most interesting about the whole construction of Fedosov quantization. We obtain the full classification of Fedosov quantization up to the equivalence relation. Namely, the following is true. Theorem. Two star products are equivalent if and only if the classes of square root of minus 1 divided by h bar omega plus phi 1 and the same class but for phi 2 inside H2 Theorem differential, Theorem cohomology of M extended by H bar coincide. I barely sketched the idea of this proof. In fact, the proof is much more delicate, because I just explained that if the question which Santiago asked was quite important, because if you want to go from, so in one direction, that is, if you know that d1 and d2 are equivalent, it is easy to see that these two classes will coincide. That's what I more or less explained. But if you want to derive the opposite fact, that is, if you know that these two elements are the same in cohomology, then there always exists an equivalence of these flat abelian connections. If you want to construct the equivalence of connections, the gauge transformation of connections, from the fact that these two elements give you the same class and cohomology, then you need to work much harder. This opposite direction is always much harder. Fedosov does it more or less by obtaining a family of flat connections relating d1 and d2. This family is obtained by solving certain series of differential equations, where you plug into so it look like these differential equations look like approximately like this. You have d1, and you want to obtain the transformation which will relate d1 and d2. So you begin with gauge transformation induced by the identity section, C0 equal to identity. And then you consider a family C of t, such that C of 0 will be equal to C0, that is to the identity. And C1 should relate d1 and d2. To this end, you consider something like the equation dc dt, which should be equal to d1 of c minus d2 of c, something like that. I'm not sure about this. I don't remember the right-hand side. And also, you need to plug into this the differential form which relates the classes of phi1 and phi2.
It's in Fedosov's book, right?
Yeah, you can find. I sketched it in my lecture notes, but in Fedosov's book you can find all the details. So it's something like this. You see lambda appears here, and then you solve the equation. Fedosov quantization has lots of interesting properties in addition to what I have just described. For instance, locally, that is, for any point x in M, if you choose double coordinates, in the vicinity of x, then you can restrict Fedosov product to this open neighborhood of x. And the restriction of Fedosov product to this open neighborhood will be equivalent to the Moyle product in the book coordinates. Another interesting fact about Fedosov quantization is that locally, no, sorry, not locally, globally, there exists a unique trace on Fedosov's algebra. And when I say trace, I mean there exists a map from a space of flat sections. That, since I identified the space of flat sections with the space of functions with the Fedosov product on M, I can actually consider just the space of flat sections on M. And the trace is a map from this space to a space of formal power series with coefficients in H bar. Yeah, with invariable H bar. And this map should verify the usual trace property. That is to say, trace of A times B should be equal to the trace of B times A. This trace is given by the integral of M, supposing M is compact. Otherwise, we need to restrict our attention to the space of sections with compact support. Take A, take its projection to the zero terms, A0, or sometimes it is written as epsilon of A. When I say 0, it is 0, just the usual function, when we omit all the elements which include y. And take the integral with respect to the top power of the symplectic form. Now one can use this formula to prove various theorems resembling the famous Atiyah-Zinger index theorem. These theorems are called the algebraic index theorems. Namely, let me very briefly outline what these theorems would look like. An element, so first of all, instead of considering just the space of flat sections and just the Weyl algebra bundles, we can introduce this Weyl algebra bundle with coefficients in certain vector bundle. So if you have a vector bundle E over a manifold M, symplectic manifold, for instance, you can do the following thing. You take M equal to a cotangent bundle of certain smooth manifold X, right? So this is smooth manifold. You have a vector bundle here. For instance, you can take this to be equal to the pullback of any other vector bundle here, right? Then you can consider the algebra, Weyl algebra bundle on T star X with coefficients in the endomorphisms of pullback of E. So locally, any section here will look like the formal sum of the elements like this. But this time, this will be a matrix valued function. You can define the symbol of such element. It will be just a function on T star x with coefficients in matrix value with matrix coefficients, right? You just replace y I by elements in T star x. Well, it's something like polynomial functions, smooth polynomial functions on T star x with coefficients in endomorphisms. And then you can define elliptic elements A as those elements whose principal symbols are invertible outside of the zero section, just as in the usual sense. But this time, these elements are not genuine differential operators. They're just some elements of non-commutative algebra. As I explained, Moyle product can be identified with Weil algebra. The algebral functions of polynomial functions on some Euclidean space equipped with Moyle product can be identified with the algebra of formal differential of polynomial differential operators on this space. And this is the same thing, but now you deal with not just a vector space, but rather with a manifold. So you can actually identify elements of Fedosov algebra when your manifold is equal to T star of x with the space of differential operators. So now you can say that elements here are differential operators on the sections of a vector bundle. You define their symbol. You can now define elliptic operators. You can define their parametrics. And then you can define their index. Index of an elliptic element should be equal to something like trace of parametrics of A times A minus trace of A times parametrics of A, if I'm not mistaken. So this is now an element in C coefficients in H bar, right, in the case of formal power series. And the algebraic index theorem consists of identifying this element with the integral of certain differential form over the manifold X. You can do this in a very natural way by unraveling all the definitions which I just briefly explained here and obtaining the classical formula by Atiyah and Zinger that this index is equal to the integral of Chorn class of the Atiyah difference construction, whatever it means, it'd be multiplied by the Todd class integrated over the manifold X.
Here, what is P?
Sorry?
Here, what is P?
P is the parametrics, PA, parametrics of A. It's an operator which is almost the inverse of the elliptic operator. It's somehow as close to the inverse operator as we can come in the space of differential operators. You can give this definition in the framework of Fedosov algebra as well. So you see, Fedosov quantization is quite an interesting thing. There are lots of things which are still missing in it. For instance, the classification of Fedosov quantization with some additional structures like Fedosov quantization of symplectic manifold with symmetries are not well known. Classification of the structure of Fedosov quantization when there is some stratification on the manifold are not well known. You see, the index theorems are pretty. There are lots of variations of index theorems. You can speak about index theorems for just one vector bundle and one manifold, but you can also speak about the index theorems for families of differential operators and families of vector bundles and so on. You can speak about equivariant version of index theorems, and all these index theorems in framework of Fedosov quantization are either not well known or there exists only some partial information about them. So I think this is an interesting subject for anybody who wants to study. But it's time for me to go from Fedosov quantization to a more general situation, that is to say, to Kontsevich quantization. Okay? I hope I'll have enough time to introduce the basic notions I need in my future lectures. So as I explained, Kontsevich quantization is the most general form of quantization known nowadays, form of deformation quantization. It can be applied to any Poisson manifold and gives, so it's a kind of a black box into which you feed the Poisson manifold, the Poisson structure in it, the bivector, and which spits out the star product formula. It can be applied to any Poisson manifold, but I think it is a bit unexpected, but in fact, it is sufficient to do this trick only for the Euclidean space. Because already in the case of Euclidean space, if you work with a generic Poisson structure, which might be of different ranks at different points of Euclidean space, the constructions known before Kontsevich do not work. And on the other hand, if you know this Kontsevich construction for just Euclidean space, then you can use a trick called the formal geometry to go from local data, which is provided by Kontsevich quantization of Euclidean spaces, to the global version of the star product for any manifold. So I'll concentrate on the case when the Poisson manifold is equal to just Euclidean space, but the Poisson structure is genuine. And then, in the end, I'll explain how to globalize this construction, well, even if you do this very briefly. Globalize. In order to to explain Kontsevich construction, let us consider again the associativity condition, the associativity equation. We have equality A times B times C is equal to A times B star C. And if the star product of A and B is equal to the formal power series of bidifferential operators BP of A and B, then I have the following equation equivalent to this one. Delta B plus 1/2 of B comma B is equal to 0, where B is the formal power series of bidifferential operators considered as an element in a space of two-dimensional cochains on the algebra of smooth functions. So that is RD for us. It's almost evident that we have this equation. Actually, I already spoke about this several times during my course, especially at our last a week ago when I described all the abstractions in a step-by-step manner, right? I obtained this equation in several different instances. Now I just collapse them into into unique equation where I deal with formal power series on both sides and generating series. So we need to find B in this in the space of formal power series of M, which I extend by introducing formal variable h bar. And let me abbreviate this just to this. Not the RAM, but differential. Rn extended by h bar. Verifying this equation, which is, by the way, called the Maurer-Cartan equation. Maurer-Cartan equation. This Maurer-Cartan equation is in fact ubiquitous in this field of study, in this branch of mathematics and information theory. And in fact, we already have an element which verifies this Maurer-Cartan equation. Just look onto the Poisson side of this story. Here we have an element pi in the space of polyvector fields, two-dimensional polyvector fields on RD, right? Which you can also formally enhance by introducing formal variable h bar. This is a bivector field, the Poisson bivector field. And since it's a Poisson, it verifies the equation and its Schouten bracket with itself vanishes. We can formally add to this equation 1/2, and then add delta of pi, where delta is the zero differential on the space of polyvector fields. So as you see, Poisson bivector verifies the Maurer-Cartan equation. And one can now rephrase the problem we are dealing with as follows. Given an element which verifies the Maurer-Cartan equation in the space of polyvector fields, restore the element in the space of polydifferential operators, which would verify the same Maurer-Cartan equation. This looks a little bit arbitrary unless you remember that there is a very narrow and very close relationship between the space of polyvector fields on arbitrary manifold and the space of polydifferential operators on the same manifold. Namely, I imply at the Hochschild-Constant-Rosenberg theorem. So by Hochschild-Constant-Rosenberg theorem, Hochschild-Constant-Rosenberg theorem, Hochschild cohomology of this differentiable complex of the algebra of functions on Rd is isomorphic to the space of polyvector fields on the same space. Moreover, the isomorphism sends the Gerstenhaber bracket into the Schouten bracket. If we had a homomorphism of algebras, so if there were a homomorphism of algebras, namely we have a map which somehow induces this isomorphism, that is the Hochschild-Constant-Rosenberg map, but it actually goes in the opposite direction. So we had this, so let's put it this way. If the Hochschild-Constant-Rosenberg map were an homomorphism of algebras, if the Hochschild-Constant-Rosenberg map were a homomorphism of algebras, then we would just take this pi, we apply the Hochschild-Constant-Rosenberg map to it, and then we would have the same equation. You see, this is a homomorphism of Lie algebras, so this would go to 0, right? If it were a homomorphism of Lie algebras, this would go to 0. And moreover, since delta commutes with chi, with the Hochschild-Constant-Rosenberg map, we see that delta of chi of p is equal to 0, so we still have a Maurer-Cartan element equal to just given by just chi of pi. Unfortunately, Hochschild-Constant-Rosenberg map is not a homomorphism of Lie algebras. It only induces homomorphism of Lie algebras on the level of cohomology. What does it mean? It means that if you have two elements, A and B, in polyvector fields. Whatever, let it be X. For a while, it doesn't matter whether it will be RD or something else. And we apply chi to A, chi to B, and we take the commutator. And this will not be equal to chi of the commutator of A and B, but instead, since chi still induces the isomorphism in cohomology, the difference will be equal to certain element chi2, certain map chi2 applied to AB. And here we need to imply delta here. And maybe we can also add delta of A, B, plus or minus, and plus or minus chi2 of A delta of B. If A and B were closed, these two last terms wouldn't appear at all, because delta of A would be equal to 0, delta of B would be equal to 0, and since we assume that chi2 is a bilinear map, then these two terms would just disappear, right? But what we can do now? What can we do now? We know that this is not true. But on the other hand, a difference chi of pi minus chi of commutator of pi and pi, that's 0, right? But still, let me restore it to its full glory. It is equal to delta of chi2 of pi, right? So this delta of this chi2 is a differential operator, right? When we apply delta, we again get a differential operator, polydifferential operator. So we can now say that the star product of A and B should look like A times B plus H bar chi of P, chi of pi applied to AB, right? But then we'll have, H bar squared, H2, chi2 of pi comma pi applied to AB. And this now looks precisely as the first equation we considered last week when we spoke about the associativity of the star product. So this chi2 is precisely this correction term we need. And we obtained it not from solving certain equation, but just from the fact that the map, Hochschild-Kosten-Rosenberg map, induces an isomorphism in cohomology, an isomorphism in the level of Lie algebras, right? Of course, this is not sufficient yet to obtain the star product in full generality, because if we look for the next term, right, for the chi3, we need to find some chi3, and so on and so forth. And that brings us the following notion. Brings forward the following notion. I'm going to omit all the details, all the motivational part of the story, and just give the definition. definition. Let G and H be two differential graded Lie algebras. Differential graded Lie algebras. We will say that we are given an L infinity morphism f from G, from G to H, if there are given maps Fn from exterior n-fold powers of G into H such that the degree of this map will be equal to 1 minus n. Oh, we're running out of time, so I just give you this definition and then stop here. Okay? And the following inequalities hold. Delta of f n plus 1, when you apply it to x1 through, let it be x0 through xn, should be equal to, there are two terms. First, you have the sum over I varying from 1 and to n, so from 0 to n, and j varying from I to n of f n xi xj x0 and xi xj are omitted. But that's not all. Plus, oh, and the sum is, and the sign here actually depends on I, j, and the degrees of all the elements which appear here. So it's very hard to write down the sign. You just need to remember that whenever you change the order of two elements, the sign appears. But then there will be the second term. It is sum for all I and j whose sum is equal to n plus 1. And again, the sum over all permutations of S n plus 1 elements. I think we need to do something like this. 1 over I factorial, j factorial, certain sign of this permutation, and also on, it depends on the permutation and also on the elements. Then you have the following thing. Fi is applied to x as 0 as I. Commuted with fj of the rest of the elements. As you see, it looks pretty complicated and pretty cumbersome. But if you look into the first few terms of these equations, you will see that it is precisely, so the first term will just give you a map from f from G to H. F1 is just a linear map from G to H. And the equation, which it verifies, just says that delta of F1 is equal to 0. That is to say, F1 is a map which commutes with the differential. So it's just a chain map. F2 is a map from the second exterior power of G, exterior square of G, into H. And if you expand this equation again, you will see that it is precisely the cochain homotopy, which relates F1 of the commutator with commutator of values of F1. And that's it, more or less. All the other terms are important because they actually give you the relation, the relation terms we need. So next time, I explain how to use this L-infinity map to obtain the Markov-Katana elements. And then I'll describe the way Kontsevich constructs the L-infinity morphism from the Hochschild-Kosten-Rosenberg map. And that actually will solve the deformation quantization problem, at least for Euclidean spaces. The globalization procedure takes a bit more time, but I'll try to very briefly explain it as well next time.